Okay, so for homework 4, part A, question 1, we are asked to use a force balance and definition of Newtonian viscosity to derive an expression for the laminar velocity profile in horizontal cylindrical tube. So, if we are considering a cylindrical fluid element of length dx and radius r within the tube, the pressure difference between the two ends creates a shear force, and according to Newton's velocity gradient, for laminar flow, we'll assume the flow is steady and the velocity is parabolic. So the force balance in the radial direction would then be expressed as T wall, minus T fluid equals dr times dr, where the tau wall is the shear stress at the wall of the tube, and then the fluid is the shear stress exerted by the fluid on its surroundings. So then for laminar flow, tau is equal to mu du dy, and recall that mu is the dynamic viscosity. So now integrating this equation into integrating this equation to obtain the velocity profile. We're going to integrate from 0 to u on the left side and 0 to r on the right. So we would have here u to 0, t fluid du is equivalent to negative integral 0 to r dr dr. It's not a d, it's supposed to be like that. Which then would become the integral from 0 to u of mu du dy du, which is equal to the negative integral from 0 to r dr, which would then become, take mu out because it's constant, from 0 to u of du, which is equal to the negative 0 to r dr, which can then simplify to mu times u minus 0 equal to negative tau minus 0, which, multiplying all of that out, we would get mu u equals negative tau, and which would then just be mu du dy is equal to negative dr. So now for Newtonian fluid, dr is constant, so then negative dr is equal to the pressure drop across the length, which is delta P over L. So then we would just set that equal to mu, so you would get mu du dy is equivalent to delta P over L. And then to solve this for laminar flow boundary conditions, where we're going to say u is equal to 0 at y equals 0, and u is equal to big U at y equals r, we can find the velocity profile, which is u of y. So we'll start by integrating both sides with respect to y. So we integrate, and we'll get the integral of mu du is equal to the integral of delta P over L dy, which would then simplify, taking both of these in front of the integral. Mu integral du is equal to delta P over L integral of dy. And then solving that out further, you get mu times u minus u naught is equivalent to delta p over L, I have space, y minus y naught. I don't know if I said u times u naught, I meant u minus u naught. Because the velocity is, u naught is the velocity at some point of y naught, which is right, those are there. So now we'll rearrange the equation to be able to solve it. And again, we're solving for u of y. So to do that, we would get u of y is equivalent to u naught plus delta p over L times y minus y naught. And using the same boundary conditions, we would then get 0 is equivalent to u naught plus delta p over L mu times L times 0 minus y naught, and then solving this out for u naught, we would get u naught is equivalent to negative delta p over mu times L y naught. And then to keep solving this out even further, we would get u is equivalent to u naught plus delta p mu L times, because remember, y naught, y is equal to r, so you could do r minus y naught. Keep solving, u equals negative delta p over mu L times y naught plus delta p mu L. This is just multiplying out the r and the y. R like that. So then if we take these equations and we solve the two equations, which will give us u naught and y naught, which can then be substituted back into the expression. So for the first equation, we'll express y naught in terms of u naught. I believe it's this equation. Let's just make this easier to see. So in terms of y naught, this one equals negative mu times L over delta p times u naught. And then substituting this into our second equation here, we would get that, bring this down here, we'll get that u is equal to negative delta p mu L times negative mu L over delta p u naught, which is what we got for y naught, plus delta p over mu L times r, which then would just simplify down, because those cancel out, and well, all of that cancels out. So then what we're just left with is u equals u naught plus r. So then again, we want u naught, so we would get u naught is equivalent to u minus r. And then if we plug this expression back in up here, we'll bring this back down in red, we would get y naught is equivalent to negative mu times L over delta p times u minus r. So that's our expression for y naught. And then substituting both of these expressions into our equation for u of y, and that down here is really bad. We would do u of y is equivalent to u naught, which is u minus r, plus delta p over L times y minus, and then y naught, which is negative mu L over delta p times u minus r. And then just simplifying this down, we would get that u simplifying this down, we would get that u of y is equal to u plus delta p over mu times L times y minus r. And that is our final expression for u of y. So for question 2 of part A of homework 4, we are asked to derive an expression for the flow rate as a function of pressure drop, fluid viscosity, and the pipe length and diameter based off of question 1. Excuse me. So we know that flow rate can be obtained by integrating the velocity profile over the cross-sectional area of the pipe. So again, flow rate is Q, which would equal the integral from 0 to r of u of y times 2 pi y dy. And so then, now using the expression for velocity that we got in part 1, we can integrate to find the flow rate. So that expression is the delta p over mu times L. So then we would get Q equals the integral from 0 to r of delta p over mu L times y dy, which simplifies down to Q equals delta p over mu L y squared over 2 evaluated from r to 0. So then just solving this out, our final expression for Q for the flow rate would be delta p over 2 mu L times r squared. And that would give an expression for a flow rate in terms of pressure drop, fluid viscosity, pipe length, and diameter. Because for question 3, homework 4 part A, we're asked to derive an expression relating the frictional heating to the flow rate, fluid viscosity, density, pipe length, and diameter, using the equations from part 2. So frictional heating of a pipe can be related to viscous dissipation in the flow, and the rate of this is, let me write this down, I don't know the name of this symbol, sorry, it's this little guy, which is equal to mu du dy du dy. So looking back to the first question and the velocity obtained, we can express this as a function of y and then integrate it over the cross-sectional area to find the total frictional heating. So it would just be, I think it's phi, I don't know, which is equal to mu times delta p over L squared. And then frictional heating can be related to the rate of viscous dissipation, fluid density, and flow rate, just by doing this. So if you do Q of H, which is equal to that, little lines, times V, times, rho for density, and then substituting in our expressions that we have, it would become mu delta P over L squared times Q over A times rho, which then can be expanded further into mu delta P over L squared times Q over pi d squared over 4 times rho. So then taking this final expression, simplifying it, our Q of H would be equivalent to 16 mu times Q delta P squared over pi squared d squared L squared all times rho. And this would be your expression that relates frictional heating to flow rate, viscosity, and density of fluid, and the pipe length and diameter.